Picture a Hiroshima-sized atomic bomb detonating. Now, imagine that happening not once, but every single second, 24 hours a day, 365 days a year. According to recent data from the Chinese Academy of Sciences and NOAA, that is roughly the amount of excess heat energy our oceans have been absorbing recently. It is a number so staggering, it almost feels abstract, until you realize that energy isn't just vanishing. It's reorganizing the fundamental operating system of our planet.
We spend so much time looking up at the atmosphere, worrying about the carbon in the sky, that we've largely missed what's happening down below. The ocean has been silently doing the heavy lifting, acting as a planetary heat shield. But that shield is cracking. Today, we are diving deep into the thermodynamics of a warming ocean. We're talking about the doubling of heat uptake, the physics of thermal expansion, and why the next superstorm might not be an anomaly, but a mathematical certainty. I'm Chloe, and this is The Deep Dive.
It is great to be here, Chloe, and that image you started with, the bomb analogy, it is violent, but it is necessary. We are dealing with energy accumulation on a scale that the human brain really struggles to comprehend.
It sounds like hyperbole, Alex. I mean, if that much heat were accumulating in the atmosphere, we'd all be dead, right? So why aren't we boiling?
Because water is miraculous. It has this incredible property called specific heat capacity. Essentially, water is stubborn. It takes a tremendous amount of energy to raise the temperature of a cubic meter of seawater by even 1 degree compared to air. So for the last century, the ocean has effectively been a giant battery, storing about 90% of the excess heat trapped by greenhouse gases. If that heat had gone into the atmosphere instead, global temperatures wouldn't have risen by 1.2 or 1.5 degrees Celsius. They would have risen by dozens of degrees.
So the ocean has been saving us from ourselves. It's the buffer.
Exactly. It's a buffer. But here is the problem. Buffers have limits. And the terrifying statistic that brings us here today is the rate of change. A landmark study published in Nature Climate Change and backed up by more recent data from 2025 showed that we have effectively doubled the heat uptake. Roughly half of the total heat absorbed by the ocean since the Industrial Revolution has occurred just since 1997.
Wait, pause on that. Half of all the heat absorbed since the steam engine was invented has happened since Titanic won Best Picture?
That is the timeline. We are compressing centuries of thermodynamic change into a couple of decades. And when you load that much energy into the system that quickly, you don't just get slightly warmer water. You get a fundamental shift in physics. You get what we call committed warming and a phenomenon known as rapid intensification in weather systems.
Let's break that down, because rapid intensification is a phrase I'm seeing in the news constantly now. It feels like every hurricane season, we hear about a storm that went from a Category 1 to a Category 5 overnight. Is that the ocean heat at work?
100%. Think of a hurricane as a heat engine. It extracts energy from the ocean's surface and converts it into wind. In the past, a storm might churn up the water, bringing cold water from the deep up to the surface, which would naturally act as a brake, slowing the storm down. But now, that deep water isn't cold anymore. We are seeing heat stored hundreds of meters deep, so when the storm churns the water, it just finds more fuel. We saw this with Hurricane Otis in Mexico a few years back, and more recently with the storms in the 2024 and 2025 seasons. They don't hit a brake, they hit a gas pedal.
So the safety valve is gone. The ocean used to regulate the storm, now it supercharges it.
Precisely. And it's not just wind speed. Warmer water evaporates faster. The Clausius-Clapeyron relation, a basic rule of physics, tells us that for every degree Celsius of warming, the atmosphere can hold about 7% more moisture. So you have these storms that are not only spinning faster, but are also loaded with significantly more water. That is why we are seeing these inland floods that are completely off the historical charts.
Okay, that explains the sky. but I want to talk about the water itself. Because when we talk about sea level rise, I think most people visualize a melting glacier falling into the sea, like an ice cube dropping into a glass.
Right, and that is a huge part of it. But there is an invisible driver that accounts for about a third, sometimes up to 40% of the rise we're seeing: thermal expansion.
Thermal expansion, high school physics, right? Things get bigger when they get hot.
Simple as that. But apply it to a basin that covers 70% of the planet. When you heat the ocean, the water molecules literally move faster and push further apart. They take up more space. We aren't just adding water to the bathtub, the water already in the tub is expanding. And because deep ocean warming is accelerating, remember that heat is penetrating deeper, this expansion is happening from the bottom up. It is a relentless physical force pushing coastlines inward, independent of how much ice melts in Greenland.
That feels incredibly difficult to reverse. You can't just cool down the Pacific Ocean.
No, you can't. And that's the committed warming I mentioned earlier. Even if we stopped emitting carbon today, right this second, the ocean has a massive thermal memory. It will hold on to that heat for centuries. It's like a flywheel that's been spun up to incredible speeds. It doesn't just stop because you took your hand off the wheel.
This paints a picture of a physical system that's losing its stability. But what about the biology? If I'm a fish or a coral reef, what does this doubling of heat actually feel like? Is it just swimming in a warm bath?
I wish it were that pleasant. For marine life, heat is a metabolic tax. Fish are cold-blooded. Their metabolism is directly tied to the water temperature. As the water warms, their metabolic rate skyrockets. They need more food and, crucially, more oxygen just to stay alive.
Okay, so they're burning energy faster.
They are running a marathon just to stand still. But here is the cruel irony of physics again. Warm water cannot hold as much dissolved oxygen as cold water. So at the exact moment these animals need more oxygen to support their revved-up metabolisms, the ocean is providing less of it. It's a squeeze from both sides. Biologists call this the metabolic index, and for many species, the math just stops working.
It's suffocation. It's not just heat stroke.
It is deoxygenation. We are seeing the expansion of what are called oxygen minimum zones, massive stretches of the ocean where life essentially can't exist. And this isn't theoretical. We've seen mass die-offs of crabs in the Bering Sea, billions of animals disappearing because the thermal conditions shifted. And then, of course, there are the marine heat waves. You might remember the blob in the Pacific a few years back.
Yeah, that mass of warm water off the West Coast. It sounded like a horror movie title.
It essentially was for the ecosystem. These marine heat waves are like wildfires underwater. They burn through kelp forests, they bleach coral reefs, and they disrupt the food web from the bottom up. And because the baseline temperature of the ocean is higher now, due to that doubling of heat uptake, these heat waves are becoming longer, more frequent, and more intense. We are moving into a state where extreme is just the new normal.
I want to touch on something you mentioned earlier about the deep ocean. We usually think of the deep sea as this cold, static, dark place, but you're saying the heat is reaching down there too?
It is. Historically, the deep ocean was our safety deposit box for heat. We thought it would take thousands of years to mix down there, but recent data, including studies using the Argo Float network, these autonomous robots bobbing around the world's oceans, shows that the deep ocean is warming much faster than we predicted. In the Southern Ocean specifically, we're seeing massive heat uptake.
Why the Southern Ocean specifically? What's special about the water around Antarctica?
The Southern Ocean is the lung of the world. It's where old, deep water rises to the surface and new surface water sinks to the bottom. It's the primary mixing valve for the global ocean circulation. If you jam heat into that system, you risk disrupting the global conveyor belt that regulates weather patterns from Europe to the equator. And recent findings suggest that the Southern Ocean has accounted for a huge proportion of the global heat uptake. It's working overtime, and we don't fully know what happens when that specific gear in the machine gets too hot.
This connects back to the buffer idea. It feels like we've been running up a debt. The ocean has been paying the interest for us, keeping the atmosphere livable. But now the principal is due.
That is a perfect analogy. We have been accruing a thermal debt, and the repayment comes in the form of rising seas, stronger hurricanes, and collapsing fisheries. The scariest part of the recent data isn't just the current temperature, it's the acceleration. If the heat uptake hadn't doubled, we might have had more time to adapt. But the doubling means the window for adaptation is slamming shut.
It's heavy stuff. But I have to play devil's advocate for a second. There are always natural cycles, right? El Niño, La Niña. How do we know this isn't just a natural spike that will settle down in a decade?
That's a fair question, and it's one scientists have rigorously tested. We do have natural variability. El Niño releases heat from the ocean to the air, La Niña buries it. But what we are seeing now is a trend line that punches through those cycles. When you look at the ocean heat content charts from NOAA or the Institute of Atmospheric Physics, it's not a wave going up and down. It is a relentless staircase going up. The valleys of today are hotter than the peaks of 30 years ago. The natural cycles are still there, but they are riding on top of this massive human-driven surge.
So the baseline has shifted. We're not starting from zero anymore.
We are starting from a fever, and that fever changes how everything else reacts. For example, look at the Antarctic ice shelves. We used to worry about warm air melting them from above. Now, we know the primary threat is warm water melting them from below. That deep heat we talked about, it's eating away at the grounding lines of the glaciers, destabilizing them in ways that atmospheric models didn't initially catch.
Which brings us back to sea level rise. If you destabilize the ice from below and you expand the water from within, the projections we saw 10 years ago might be practically useless.
They were conservative. That's the consensus now. We are seeing processes accelerate faster than the models predicted because we underestimated the ocean's efficiency at moving this heat around. We are entering a period where historical data is no longer a reliable predictor of future risks. Infrastructure built for the sea levels of 1990 is simply not going to survive the physics of 2040.
Alex, we've covered the physics, the biology, the weather. It's a lot of bad news. But understanding the mechanism is the first step to dealing with it. Is there any aspect of this heat uptake that offers a glimmer of hope? Or is it purely a runaway train?
The glimmer of hope lies in the same physics that got us here. Because the ocean has such a high heat capacity, it stabilizes the climate. If we can stabilize our emissions, actually reach net zero, the ocean will eventually stop warming. It won't cool down fast, but it will stop getting worse. The flywheel will stop accelerating. The lag time is long, yes, but every fraction of a degree we prevent from entering the ocean is energy that won't be there to fuel a superstorm in 20 years. The system is sensitive, which is dangerous, but it also means our actions, stopping the input of carbon, do have a direct, measurable impact on that heat curve.
It's a powerful reminder. The ocean isn't just a victim of climate change, it's the engine of it. And for a long time, it was our silent partner, taking the hits for us. Now it's telling us, quite loudly, that it's full.
It is. The silence is over. We are in the era of consequences, and the ocean is the messenger.
Alex, thank you for making the invisible visible for us today. It's a sobering perspective, but one we absolutely need to have.
Thank you, Chloe.
This conversation changes how you look at the water, doesn't it? It's not just a blue expanse anymore. It's a battery, charged up and waiting. The heat is there, the physics is set, but what we do next still matters. If you found this deep dive valuable, pass it along to someone who needs to understand what's really happening beneath the surface.